Today I will first finish the discussion of yesterday. I really wanted to arrive at just this nice piece of linear algebra, just some explicit matrix, and describing explicitly its eigenvectors and eigenvalues. So what we're discussing was Gromov-Witten theory of some complete intersection X inside some projective space, and we're, let's say, of dimension M, and we're looking at V, its primitive cohomology, so primitive part of the middle dimensional cohomology. On this thing we have the intersection form. And for simplicity, I was looking at the case where it's M is even, so that this form is symmetric. And then we were looking at some family of Gromov-Witten invariants where we were fixing the insertions coming from the ambient projective space, we were fixing the psi classes, and we were varying the primitive insertions. So assuming that we had 2n primitive insertions, then we had some element GW, which was some linear form on V on 2n variables. So in other words, it was an element of V tensor 2n joule. And the main point was that this thing was invariant under the orthogonal group for this symmetric intersection form. And then I reviewed the description of invariance of the orthogonal group. So in particular, we had this space of invariance. We had a map from the vector space generated by n pairings, where it's to form n pairs on 2n elements. This map was surjective. And to describe the kernel, I describe the fact that this thing, as a representation of the symmetric group, has a natural decomposition into irreducible representations of a symmetric group. So it was the sum of a partition of 2n. And the partitions which appear as the one which have even parts, so the corresponding Young diagrams are rows of even lengths. So m lambda, so this thing I call it phi maybe. And the kernel, the point of this description was that the kernel could be described explicitly as being the pieces in the decomposition where the length of lambda was at least dimension of V plus 1. Okay, so the thing we care about was here. And the point, so we know the kernel, so if we forget about the kernel, you can really identify this space with the space here on the complement piece of the direct sum decomposition. Okay, and then what's this? So the general idea is that we wanted to trade these primitive insertions, these 2n primitive insertions, for n nodes in the domain curves. So if for every p n pairing, so for every p in this set of n pairings, we constructed some nodal Gromov-Witten invariants depending on this pairing. So this thing was just a number obtained by counting curves exactly of the same kind as the curves that we are using here to define these Gromov-Witten invariants, with the main difference that the 2n points at which we insert the primitive insertions, they are identified together according to the pairing to create a curve with n self non-separating nodes. So this thing is a single number. And then the main statement was that if you know all these nodal Gromov-Witten invariants for all possible n pairings, then you can recover all this family of Gromov-Witten invariants with any possible primitive insertions as a 2n mark points. And the point why this thing was true was following from the splitting formula in Gromov-Witten theory, saying that this invariant with nodes is the same thing as the invariance without nodes, where you open the nodes to create two mark points. And then geometrically, to get the same number, you want these two mark points to map to the same point inside the target space X. And so to impose that in the Gromov-Witten language, you insert the class of diagonal as these two mark points. So the statement what this thing is equal to this linear map evaluated on the tensor obtained by taking the tensor product of the pairs in the pairing and the corresponding diagonal. So here I have the diagonal. So here I'm really looking to the piece of the diagonal, which is in the primitive cohomology times primitive cohomology. There is also lower order part, but I forget about it. Okay, so we know this multilinear form evaluated on all these tensors, and the claim was that it uniquely determines this multilinear form. And the reason for that is that the diagonal on V, actually, it's equal, so maybe I wrote like this, it's really equal to the inverse of the intersection form. Okay, so if you're insisting, it's one way to write the formula for the QNet decomposition. Of the diagonal. Okay, so this thing is just a very general fact that you have the class of diagonal of a space inside cohomology of the product, which is a tensor product of cohomology with itself. Maybe I write, okay, if I just have, okay, cohomology of X, and one way to write it is that if this thing has a basis, EI, and if I denote by eta ij the intersection form, and I use a tensor notation eta ij indices up for the inverse and for the components of the inverse. Then the class of the diagonal inside cohomology of X cross X, cohomology of X, tensor cohomology of X, is just equal to sum over ij eta ij ei tensor ej. And then yesterday we said that because this thing essentially generates the invariance of the dual space, then by general duality between invariance and invariance of the dual space, if you know all this thing, you can recover this thing. So what I wanted to just describe briefly now is to write down actually this thing explicitly. So what I mean by that is that this Gromov-Witten, okay, I want to look at this operation evaluating on the diagonals, just apply it to any element inside this space, and just write down in this space as a natural basis given by pairings. So I just want to write down the matrix that you obtain when you do that. So what I mean is that for every, so here for every pairing, now let me call Q a pairing in N, then add this map. Q goes to the corresponding tensor here that I was denoted alpha Q. So now I want to look for every pairing Q and every pairing P. I want to look to this invariant tensor evaluated on, okay, I call alpha Q, evaluated on the diagonals given by the pairings P. Okay, so this thing will be the coefficient of a big matrix, this thing a coefficient of a 2n minus 1 double factorial times 2n minus 1 double factorial matrix. So just the matrix that you get when you insert these diagonals inside these generators of the space of invariants. And this claim of invertibility is related to the fact that this matrix is exactly non-degenerate in the piece which is orthogonal to the kernel. So this thing follows from general arguments, but I just want to see it explicitly. So what is this matrix? The claim is that this number is just some elementary tensor algebra. This number is dimensional V to the power the loop number between the pairing P and Q. So L of PQ, loop number of P and Q. So P, it's an n pairing. It's a way to create n pairs out of two n elements. So it can be represented by some arc diagram where I represent the elements which are paired together. And to define this number, I draw similarly the arc diagram of Q, except I draw it on the lower part of the blackboard. So maybe Q pairs this point with this point and this point with this point. And then when I glue these two arcs diagram together, I get a union of loops, and I just count the number of loops. So in this picture, the loop number is 1. And why this thing is true, somehow it's just some contraction of tensors, that this invariant tensor is made of the symmetric forms of the tensor eta ij, whereas this delta is made of the inverse tensor. So there is a thing like eta ij, eta kl, and you just need to contract these tensors. And each time you have a loop, it means that you can contract the tensor in such a way that you get a trace of 1, and you get the dimension of the space. So this thing is just contracting the tensor, inverse tensors according to the pairing, you just get this answer. Okay, so here it's a completely elementary to define matrix. So the notion of pairing is a completely elementary combinatorial notion, and you can just look to the corresponding 2n minus 1 double factorial times 2n minus 1 double factorial matrix whose coefficients are given by this formula. Some number powers the loop numbers. Okay, so for example, if n equal 2, so that 2n equal 4, then this matrix, let me call it M. And if, let's say, to simplify, let me call it X for dimension of V, then it's a 3 by 3 matrix. There is three ways to pair 4 elements. And if you compute the loop numbers, you find this 3 by 3 matrix. So actually, here it's not so complicated, but already the next case is a 15 by 15 matrix. So it starts to look bigger. And so the thing I wanted to state is that actually, so to see explicitly this reconstruction result, I simply want to state the spectral decomposition of this matrix. You have this very explicit matrix. You can ask what are its eigenspaces and what are its eigenvalues. Okay, so it's a completely elementary question. So for this 3 by 3 matrix, it should not be difficult for anyone. But already, if you look to the 15 by 15 matrix, it might not be so obvious. So the theorem, which has been proved by many different people in many different contexts, so maybe that's been proved by Alan Wiles. And actually, this story appears in McDonald's book on symmetric functions. And there is a different proof by Singesta and maybe by some other people. So I can think to this matrix, so it acts on the space generated by pairings. So it's really a matrix on the space of pairings. And this space has this natural decomposition according to the irreducible representations of the symmetric group. And the theorem is that this decomposition is an eigenspace decomposition for the matrix. And the eigenvalue on the eigenspace M lambda has a very nice formula as a product. So I will need to explain over the boxes of the Young diagram of half the partition lambda, and then dimension of V minus I plus 2j minus 1. So what does it mean half of lambda? So by assumption, lambda has even rows. So it's a partition where all the parts are even. So you can just divide everything by 2 and you get a new partition that I denote by 1/2 of lambda. And then ij are just, so you have a Young diagram for this partition, and for this formula to be correct, I is some index running from, starting from 1 and going like that, and j is an index going like that. Okay, so here this is very simple to define matrix, just involving how to glue pairings together. And the eigenspaces and eigenvalues involves this nice theory of the representation theory of the symmetric group.
But do you understand this? For the theorem, you don't really need to go to these details.
Exactly. If you just
for computer problem, eventually run, it's only for this.
Exactly. If you just want the statement is non-degenerate, then it follows from general theory. Yeah, exactly. Yeah, if you want to write down something explicitly and
to have a computer program.
Yeah, let's say if you want to have some, for example, but. Yeah, and actually the real reason why I'm studying that is because I think it's a nice story, but indeed, for the theorem itself, you don't really need. And so indeed, here the observation is that these explicit eigenvalues, indeed you can check it is a 0 on the kernel of phi, and it is non-zero on the other part. So indeed the fact that it's non-degenerate was saying that this thing was non-zero on other summands. Okay, so the exercise is to check this formula on this matrix. Okay, so now we'll kind of change subject. So here I give maybe too much detail on how to go from these invariants with possibly primitive insertions, or to eliminate these primitive insertions to form nodes. And the whole point of doing that, as explained in Hülya's first lecture, was that primitive insertions do not go through some degeneration argument, but these invariants with node, they do. So we have this picture of our complete intersection X degenerating into a union of two varieties, X1 and I think it was denoted X2 tilde, glued along a smooth divisor D. And X2 tilde was some blow-up of some X2 along Z. And the point was that X1, X2, D, and Z were all complete intersections of either lower degree or lower dimension than X. And so our Gromov-Witten invariants involving curves inside X, the general idea of degeneration, you want to follow this curve, see what they become on the special fiber, and then hope to express it in terms of the geometric pieces making the special fiber. And the point was that the primitive insertions living here, they do not extend to the total space, so they do not make sense on the special fiber. But now these invariants with fixed, where the nodal curve is constrained to have some fixed collection of nodes, this thing is a geometric condition which makes sense on the special fiber. So you might hope to have some degeneration formula which will compute Gromov-Witten invariants of X. So now we need these nodal Gromov-Witten invariants. So with no primitive insertion. So in terms of what? In terms of counts of curves in the special fiber. And if you have a curve in the special fiber, you might opt to break it into a curve in x1 and a curve in x2. But you need to remember the information how do they glue along this divisor. So what will really enter will be relative Gromov-Witten invariants of the pairs, the variety x1 with the divisor d, and the variety x2 tilde with the divisor d. And in fact, a nodal version of this story, we want to still impose nodes in the domain curves. And once we have this degeneration formula, once we have separated the two pieces,
and to be non-primitive, we're going to go to points on tangents points on devices only, yeah. This will be still, I think, will be primitive insertions and
yeah,
maybe non-primitive on divisor. Yeah.
Exactly. Yeah. Exactly. So here it was no primitive, but yeah, you need all of them because
not exactly all of them.
Yeah, you only need like enough to have the diagonal of the device. Which is why in the general procedure, then we need to iterate for the various pieces and get rid of the primitive things and do it again. And then, so I will not say much about that. I want to say something about the fact that here we will have relative invariance, so curve on some variety with some tangency condition along the divisor, with imposed nodes in the domain. And for the induction to work, we want to remove the nodes. We want to go back to something without nodes. The whole point of the node was just to go through this degeneration, and then we want to remove the node. So what we need with the splitting formula for relative Gromov-Witten invariant. So what I want to spend time on is to explain what the splitting formula is. And the point is that it will be almost the same as the usual splitting formula, but I want to explain what is the subtlety involving the relative parts. So to explain the subtlety, I want to review or describe how relative Gromov-Witten theory work. So from now on, I'm coming back to like general notations. If you have X, some smooth projective variety, and D, some smooth divisor in X, and then I have X, D, my smooth divisor. And what you want to do in relative Gromov-Witten theory is counting curves in X. So if I have a curve in X, if everything is nice and generic, this curve will typically intersect D in finitely many points. And I want to possibly impose tangency conditions for my curves along the divisor. So more precisely, if I fix some genus, some curve class. Let me fix n and m. I will explain in 1 minute for which reason. And fix mu, a partition of the intersection number of the curve class with the divisor. So I have sum over mu I equals beta dot d. And the kind of space of curves that you want to look at is a space of stable maps, genus G stable maps with, I will choose n plus m mark points. Maybe I wrote like that, I don't know. So this thing should be an ordinary stable map of genus G of class beta, but I want the intersection with the divisor. So I want the preimage of the divisor on my curve to be, first of all, I want it to be a divisor, so I want the curve to intersect the divisor in dimension 0, and I want this divisor to be the divisor of these mark points yi with multiplicity mu i's. Okay, so in this picture, the xi, maybe I draw some picture again. I have d, x, some curves. The xi are just some mark points away from the divisor. And the yi are mark points that I want to be the intersection point of the curve with the divisor. And here I want the contact order of the curve with the divisor to be fixed and to be equal to this integer mu I. So here I have fixed contact order. Mu I. Okay, so definitely you can consider this space of stable maps satisfying these intersecting the divisor nicely according to this tangency pattern. But the main issue is that this space in general is not compact. It's not proper. That's the problem. Not proper in general. So you can definitely have a family of curves intersecting the divisor in a bunch of points, but in the limit, for example, the curves could map entirely to the divisor. It is one phenomenon which could happen. Just if you have a family of parabolas, in the limit it can become a double line. All the contact points could come together, and the condition on the contact orders could be no longer respected. So the question is, how do you get around that? How do you produce a nice compactification? And so there is something naive which doesn't work, that this thing lives inside the space of all possible stable maps. So something very naive could just be the closure inside this space. But it's a very bad idea, because when you take this kind of operation, there will be no virtual smoothness of the resulting thing, so it will be a bad thing. So one way, so what we want is to produce a nice compactification. And this nice compactification will be the moduli space of relative stable maps introduced by Jun Lee around 20 years ago, at least 20 years ago. And so what is the idea is, in your moduli space you want to add objects to compactify it. And what the kind of objects you want to add are relative stable maps. And the point of what they are is that they will be mapped from a curve but not necessarily to x, but you allow the target to be modified. You allow the target to be not necessarily x, but to be what I denote by x bracket k, which is a k expansion of x along D. It's not there. So let me describe what this thing is. So if you have x and d, some very general construction that you can do is a deformation of x, is deformation to the normal cone. Okay, and the very general construction looks as follows. You start considering a trivial one-parameter family of x. So here is A1. Is x, which contains the divisor d. I start with a trivial family. And then you look over a particular point, let's say 0 in A1. And over 0, you look to the copy of d, which is inside the copy of x, which is over 0. So you consider d cross 0. It is something of codimension 2 inside the total space. And so you can just blow it up. So you blow up, and when you blow up, what happens is that you produce some, so the blow up does nothing away from 0, and what it does over 0 is to produce a new fiber, which has a new component, which is an exceptional divisor, which is the projectivization of trivial line bundle direct sum the normal bundle to D in X. So this thing is a P1 bundle, over D, and it is glued to X along one copy of D. So here there is one copy of D. But it contains a natural other copy of D corresponding to the other section of this rank, other segment of this rank 2 vector bundle. So here there is another copy of D. Here, this thing is also isomorphic to D. And this expansion, so this X bracket 1, first expansion of X along D, is a special fiber of this geometry. So it is this variety consisting of two irreducible components, one which is just X, and another irreducible component which is some P1 bundle over D, which is glued to X along D, and which has a natural other section isomorphic to D that I denote D infinity. And the K expansion is just obtained by iterating this process. So the K expansion is just a variety with K plus 1 irreducible components, one of them being isomorphic to X, and the others are all P1 bundles glued to each other along various copies of D. So this thing is the original D in X, and this thing is another copy of D, this thing is another copy of D, and I have some kind of final picture, final divisor, D infinity in this picture. And now what is a relative stable map? So it's a map from C to some xk for some k. So when k is 0, it's just some ordinary stable map to X. But now I allow the x to be replaced by this degenerate picture along D. And so I have some curve mapping there. And what we want, so there are various conditions for that to be a legit relative stable map. You want no component of your curve, so no component of C mapped to the singular locus of this geometry. You don't want any component of your curve to be mapped into one of these copies of D. You want the curve to intersect each of these copies of D in finitely many points. And you also want some nice gluing condition. If you look at one of these points on the singular locus, then by assumption it's an isolated point on the curve. It's just a node. So if you look on one side, you have a curve which has some contact order with D on one side, and on the other side you have another curve which has another a pretty different contact order, and you want these two contact order to match. So you want matching of contact orders. And finally, this condition that you wanted in your original condition, that your curve intersects with divisor D according to a nice pattern, now you impose this condition on this last level at D infinity. So you want F inverse of D infinity to be this nice divisor of my point with the correct multiplicity. Okay, and so the idea of this construction is that if you have something in this moduli space, and if you have one parameter family, and if the limit is kind of bad, that for example the curve is falling into the divisor, then the claim will be that if you create one of these geometry, you replace x by adding one of these P1 bundle, then there is a natural limit where the curve does not fall into the divisor, but instead it falls into this P1 bundle.
But you should model by protocol of geometry.
And indeed, you need to identify. So if you want some separated thing, you need to identify maps related by the natural, let me say, C star to the K action. So on each of these P1 bundles, there is an obvious C star action just scaling the fibers of the bundle. And so you have one copy of C star acting on each of these levels. And if these two maps differ by the C star K action, you want to identify it.
And it should be free. This also action. This should be, in each picture should have something non-trivial inside. It will be that's condition.
Yeah. So I guess I want to say what stable mean.
Yeah.
So stable means I want finitely many automorphism where I also count automorphisms of the target. Indeed. So now, yeah, should I ask the stable? It's like finitely many automorphism, where automorphism is the pair, one automorphism of the curve and one automorphism of the target, one of this is the automorphism which commute which is other. You want finitely many such pairs. So in particular, it's forbid like empty bubble because then you could add by C star and it will contradict that. Okay, and so the upshot of this construction is that there is a nice moduli space M bar G. So in total, let's say there is n plus m mark points, beta. Then there is this X-ray data of this partition, the tendency along the divisor of X relatively to the divisor D, so of relative stable maps. And then the point is that this is a correct definition. This thing is as nice as usual moduli space of stable maps. This thing will be a proper Dellin form. So before coming to the splitting formula, I will just and then you use this deformation series thing to produce the class upstairs. And now what I want to describe is just the same diagram for moduli space of relative stable maps, which is not the original construction of Junli. So the original construction of Junli is a bit complicated, but there is various ways to present this thing, and so I will present the one due to Abramovich, Kahneman wise. And just the general idea is, okay, so I have this moduli space of relative stable maps, and I want to work relatively to something. And the very general idea is that you should always work relatively to moduli space of maps to some kind of universal target. Meaning a variety is always sitting over a point, and pre-stable curves, they are just pre-stable maps to a point. So this thing is like a trivial statement. But maybe slightly less trivial statement is that any pair of a variety with a Cartier divisor is sitting over some universal object, which is a stack A1 mod GM with a divisor 0 mod GM. The thing is just affine line. So let's say C star, so it's a stack quotient. And if you want this map, so like maybe a point divided by GM just classify line bundles, and A1 divided by GM classify line bundle with section. So if I have some effective Cartier divisor, there is a corresponding line bundle and the corresponding section. And this thing is this map. And so you should work relatively to the moduli space of relative stable maps to this Artin stack. So the point is that the definition of this relative stable map can be, with this expansion, can be extended for this geometry. And you just work relatively to this space. And now again, the key point will be that this space will be equidimensional. And here there is natural relative perfect obstruction theory, just given by now the log tangent space. Maybe I just wrote T of xd, just vector fields with a first order 0 along T. And now you can make the same definition. So m bar gn plus m beta xd is a pullback of the naive virtual class here. Okay. So the point of that was just to make some kind of advertisement for this idea that you should always work relatively to some universal target. So if you just have a smooth divisor, the universal target is this A1 divided by GM. But if you have a more complicated situation like normal crossings divisors, and if you start doing like logarithmic Gromov-Witten theory, then this thing will be replaced by some kind of more complicated toric stacks. And so once you have this virtual class, as usual, you can define relative Gromov-Witten invariants. But with the caveat that usually to pull back homology class, you want to evaluate at some mark point. But now your map is not a map to x, it's a map to possibly some expansion of x. But there is always a natural projection from this geometry to x. So you can always evaluate for this composition and get some honest evaluation map to x. And then, as usual, you can take homology classes here, pull them back, and integrate against the virtual class. Now I'm coming to the last thing that I want to talk about, which is the splitting in this relative context. So let me consider, for example, domain curve which have a self intersecting node. And in the usual not relative story, you just open these nodes. You create two mark points, and you want to say that these two mark points map to the same point, so you insert the diagonal. But now that we're in this relative situation, this picture map to something which could be an expansion of x. So now these nodes could be on some curve for 2 points to be the same in such a thing is not the same thing as for the 2 points to be the same in the projection to X. Okay, so if I just have 2 points inside the P1 fiber, they project to the same point, but they could be different inside this P1 fiber. Which is why some of the naive version of the splitting formulas, where you will insert the class of the diagonal coming from X, is not the correct thing because of this phenomenon. So, but you just need to correct it by this phenomena. And to do that, I will draw a picture, which actually for some reason Alex and Veronica decided to put on the poster of the conference for some reason I maybe do not fully understand. So, so the picture is that if you have a space X, pair of points, they are just elements of X cross X. But now if you have a pair XD, and if you want to consider a pair of points inside this relative geometry X relatively to D, and what you should do is to consider a space that I call XD squared, which is, so it parameterizes a pair of points, but each time you have a point going to D, then you create a P1 bundle. Or 2 points going to D, you create another P1 bundle. So you do the same thing as you do for a relative stable map, but you just do it in this much simpler geometry of points inside X relatively to D. And so the picture, and so the claim is that this thing that I just described, forming bubble, explicitly it's something very simple. It's just a blow up of D cross D inside X cross X. And so the picture is, if I just take X equal P1, D equal to a point. So maybe here is some kind of picture of P1 cross P1. And here I need to blow up the point inside P1 cross P1 corresponding to 0 times 0. So when I blow up, I get this kind of picture. So this thing is P1 cross P1 blow up in a point. And then what is in the picture is just representation of what are the various points, what are the various configuration of pair of points parameterized by this picture. So it's a general point. I just have P1 with a divisor. So 0 is a divisor and just 2 points. And then on this boundary, I have, for example, the point 1 trying to go towards the point 0. And because of that, you create a bubble. So 0 and 1 come together, and 2 is left alone. Here you have the opposite phenomenon, where maybe 2 try to go to the divisor, and 1 remains alone. Here you have some special points where now 2 try to go to this node. I guess you get something like something like that, I think. And then at the general point here, you have 0, 1, 2, all on the same P1. And here you see here you have P1 with 4 special points, these 3 mark points, and this 1. So there is a P1 of such a thing, which is exactly this exceptional divisor of this blow-up geometry. And now what is the point of this picture is that what we care about is a locus where the points come together in this splitting story. And so the locus where the points come together, it is this locus. It is a strict transform of the diagonal in P1 cross P1. So such a point, I have 1 and 2 coming together. And so here I have the point I care about, which is there is 1 expansion, but 1 and 2 are together. Okay, so this subtlety, so one way to rephrase this subtlety.
And also this point you should consider as infinite on P1, which you. Because this P1 which you add has 0 and infinity, yeah?
Actually, here there is only 0 in my picture. I choose the divisor to be 0.
It doesn't matter. No, but after you blow up, it's in general picture.
Yes.
You add, on this P1 you have kind of like 2 distinguished points.
Yeah, here and here.
No, on P1 which you add.
Okay, yeah, sorry.
This in this function, and your points. Okay, so sorry, no, they can, maybe I'm wrong, they can go to infinity, yeah.
Yeah, I think so. So I don't know, on this picture you have like just 4 points and they form a P1.
I see, yes. So it's not
And so this main subtlety is that somehow the correct diagonal is not the full transform of the diagonal, but it's just the proper transform. Okay, so the correct diagonal. Yeah, and the point is that there is some evaluation map. If you have two mark points, then you have some from the moduli space to this, like some kind of refined moduli space of pair of points. And so the correct thing is like a strict transform. Okay, and so of course it's some kind of general theme in, I don't know, intersection theory, or that you should be careful of making a difference between full transform and strict transform. It is what you see here in this very specific example. And so the upshot is that there is a formula which tells you that if you have some kind of relative, some kind of nodal relative Gromov-Witten invariant, then it is equal to like some usual relative invariant with insertion of the diagonal inside X cross X. Yeah, and the key reason why you don't want to work only with this modified diagonal, why you really want to express it as a difference between the full transform and the exceptional divisor, is that the usual diagonal has a QNet decomposition, a nice QNet decomposition, whereas it will not be true for this strict transform. So you write it as something which has a nice QNet decomposition, usual diagonal, and then plus corrections. And these corrections, so they have to do with this thing, they just have to do with Gromov-Witten theory of this P1 bundle. Okay, so they involve Gromov-Witten theory of this P1 bundle over D. And then working on this P1 bundle, after enough work, you can reduce this to like Gromov-Witten theory of D. Okay, so after some work, get some kind of Gromov-Witten. Okay, so in the general argument, you need this step. So once you degenerate, you have these nodal relative things coming from the degeneration formula, and then you want to come back to ordinary invariants. With our nodes, you want to open the node, and then you need to apply this formula. Yeah, and this thing is a picture which is in the conference poster. And I will stop there. Thank you.
Any question or?
Oh, very good. There's also some works by Giventhal and Coates, this formalism of quantization of cones, Lagrangian cones, which supposedly should give also control of at least something, yeah. Maybe not, not primitive invariance.
Yeah, I don't know how to use it to control primitive invariants.
Yeah, maybe it controls non-primitive, kind of parts coming from projective space, as far as I understand.
But even for the part coming from projective space, it's not enough to find everything, right?
Not everything,
because it's not semi-simple, but yeah, somehow. Yeah. I mean, for example, it's useful. For example, if you do this like very concrete thing, like going from a P1 bundle to a base of the P1 bundle, then this formalism is quite useful to describe our Gromov-Witten of the P1 bundle. How is it related to the Gromov-Witten of the base? Then you can write some kind of nice function, and then you say you quantize this function. It's formalism. It is a way to find that. But yeah, for the point of view of Gromov-Witten of complete intersection, I don't know really what can be used to.
One second. Zooming out a little bit more. So, should I be imagining that there's sort of a universal Gromov-Witten invariant, which is a map from the tensor 2n to itself, or maybe to some other vector space, and then you can do insertions by, pairing it, by contracting it with tensors corresponding to the insertions, and the you know, when you have this pairing, like for the, you know, the nodal Gromov-Witten invariants, that's just like an example of one sort of contraction you can do. And then the actual Gromov-Witten invariants you care about are a different sort of contraction where you're like filling in with.
Yeah, that's why we have this GW, which has some kind of multilinear form containing the information about all the Gromov-Witten invariants by inserting various things. And the claim is just if you insert these particular diagonals, these particular contractions, it's enough to recover everything.
Okay. Sorry, can you say again the thing that gives you all of them?
I don't know, it was just some multilinear, I don't know. I mean, in this talk I just call it GW, but it's just some stupid name. Yeah.
And GW is a map from?
Yeah, it was a map from V tensor 2 and just to C, just taking the insertions and producing the numbers you care about.
Oh, sorry, I misunderstood. I see. So, okay. I was wondering what, okay. So the insertions are sort of are on one side of it.
Yes, on one side, yes.
And then the
invariant on the other side.
Yeah. Can you do, so I guess can you sort of uninsert from the other side and then, you know, so you have slots both for the contractions that you're doing and then also contractions for the
yeah, no, I don't know it.
Okay, so let's find Pierrick again.
Thank you.